Now, magnetic fields are more useful within the context of particle accelerators in changing the direction of charged particles than they are in actually accelerating them. So if we consider a single charge moving at velocity v perpendicular to a uniform magnetic field, and then we can play the button here. And there will be a force in the moving charge due to the interaction of its own magnetic field with this external magnetic field. And what we want is a way of working out the direction of this force. The direction of the force is perpendicular to both B and V, which are both in the plane of the screen, we can see here. And then we can use what's called the right-hand rule to work out the direction of the force. So a charge of negative Q moving with velocity V, right, then we can work out the force out of the screen. And here's the right-hand rule, basically. So the thumb represents the thrust or the force. The first finger represents the field, and the second finger represents the electron current. So you ignore the S there, but you can take the next two letters, EC, and you get electron current. So in this example here, your field is pointing from right to left, roughly, sloping up a wee bit. The actual electron current is moving down the way, and therefore your thumb at that point would be pointing out of the piece of paper or out of the screen, and so the force would be out of the screen. It's much easier to show you this in reality. If it is a positive charge that's moving rather than a negative charge, then you just stick with the right-hand rule. Don't try and learn a different rule, but just at the end, flip the direction of the force. Okay, so it would be into the screen. And there's no change in the size of the velocity in these magnetic fields, only a change in the direction. What happens if the charge is travelling parallel to the field? Then there's no actual force involved at that point, is there? Now, we don't go into great detail of describing why that is and so on. The movement of the charged particle must cut the field lines though. And we use the letter B for the strength of the magnetic field, and the size of the force F depends on the charge Q, strength of the field B, and the velocity V. B are X and V are all vectors. And the unit of the magnetic field strength is Tesla, although 1 Tesla in reality would be very strong. But we'll not do any numerical calculations involving that.